So the acid, they all have the H plus, the protons, but not all the acid the same. Some acid give you plenty of a very high concentration of the protons, and that makes them very, very reactive. So this we call them strong acid. They are more reactive, more capable, more power. And that is because those molecules, those chemicals, they almost 100% completely become ions. The hydrochloric acid is a good example. When you put the hydrogen chloride molecule into water, 100% of those molecules will fall apart. So basically, water will take the proton from the hydrochloric acid and become hydronium. And once HCl loses hydronium, loses hydrogen, it has only the chloride ion remains. So this is 100% become ions. And that's what we call them strong acid. And the bracket in this chapter we use to represent molarity. The molarity we mentioned last time. Molarity, it should be the mole of solute divided by volume liter solution. The bracket means the molarity concentration. Since the strong acid completely become ions, then the concentration of the proton or hydronium, it is the concentration of the acid. So if I say the reagent in the lab, it labels 1m HCl, 1m hydrochloric acid. So we know in 1 liter of the solution, there should be 1 mole of the HCl. But HCl, since it's strong acid, there's no more HCl molecule in water. Instead, you have in 1 liter solution, you have 1 mole of the hydronium ion and plus 1 mole of the chloride ion. And you have water molecules. What really matters for the solutions, you have basically 100% dissociated. All the H in the HCl becomes hydronium. And the remaining is the chloride. So 1m of HCl, it actually means, since we learned about chemistry, there are, in 1 liter solution, there will be 1 mole of the hydronium ion, which make it very, very acidic. And the remaining is the other part, the counterpart, negative charge ion will be the chloride. You also have exactly 1 mole. And so the strong acid, these two would equal. The hydronium concentration equals the acid concentration. That's where it comes from. And so what are the strong acid? The strong acid, quite a few, but normally I will not ask you to memorize the strong acid. In the future, any question, if it's some kind of a simple questions, basically we'll use one of those 6 strong acids. Only 6 strong acids. In Chem 1B, you'll be learning what to make the acid, strong acid. But not here. We just kind of wish you know a few compounds that are a strong acid. So here
for Chem 1A, do we need to memorize it if we go to Chem 1A?
Chem 1A, I will not ask you to memorize a strong acid. It's good to memorize, but 1B, you are supposed to know this very well. Yeah.
Okay, so not 1A then.
Not so much in 1A. Yeah, not so much in 1A, but depends on the instructor. Some instructor has their own preference. But in 1A, there's so much to learn. I will not let you stress out on this part. Yeah. Okay. And then the name of the acid. Okay, name of the acid we learned it quite a while ago. These come from the IDE ions. This whole group comes from the IDE ions. The iodide, bromide, chloride. So the acid is hydro. And you put the stem of those words, the chloro, bromo, iodo, and so forth. and ic acid. So that's about naming those acids. And the lower part, these are the strong oxy acids, nitric acid, sulfuric, perchloric acid. This is perchloric because it has one more oxygen than the chlorate. So this is perchlorate. The acid will be perchloric acid. These are all very strong acid, and the dissolving water 100% become ions. And this is you can buy from store. It is a very strong acid for cleaning the very heavy stains, very old mineral stains. It is good to dissolve the mineral, the inorganic stains. Organic, oftentimes because oil, fat accumulate, this will not work. Okay. The organic stains, because they are non-polar, relatively non-polar, much better dealt with if you use some solvent, the organic solvent, like nail polish or the gasoline for deal with organic stains. Inorganic stains oftentimes come from the carbonate. So that is easy to be dissolved by the strong acid. So these are strong acid. Later we have some question about the strong acid, how to find pH. So we need to know what acid is this. Okay, there are hundreds of thousands of acids. So except those 6 or 7 strong acids, all the other acids are weak. And the reason why they are weak, because those acids, even though they can donate H+, but to a very, very small degree, very, very small fraction. Small fraction of this will become the protons. And so this is the, we use the illustration, HF molecules, which is a weak acid. And dissolving water, most of the HF molecules stay as molecules, do not fall apart. Only 1 out of many will become, so here is basically 1 out of 4 HF molecules become ions. Very small percentage. So if 1 out of 4 dissociate, we're talking about 25% dissociate. And there are many, many weak acids. The percent dissociation is even lower, around 1% or even below the 1%. Those are fairly weak acids. And since the those kind of acid, very small percent becomes H+, hydronium, the chemical reaction as an acid for those compounds will be very slow because the concentration of the hydronium is so low, reaction takes a long time. If you remember the solution, we did the egg in the osmosis. Egg in the osmosis is a good example. So if you remember in the demo, the egg was dropped into a cup of vinegar. It takes about 1 hour for the acetic acid, vinegar, to dissolve the eggshell. Same egg, if you put in strong acid, like the one previous slide showed the strong acid, that works. It'll take about 1 hour, half an hour for the eggshell to dissolve, much, much quicker. And with a weak acid, it takes it over basically 1 day and night, 24 hours to completely dissolve the shell. So that's what a weak acid. And so the weak acid, most molecules stay as molecules. So basically this illustration shows you 3 out of 4 stay as molecules, do not dissociate. Only 1 out of the 4 become free ions. And this is hydronium. Because of water, it is hydronium. And the other part is an anion, come from the acid. So that's weak acid. And there are a lot of weak acid. So it's kind of a highlight what is interesting. The strong acid, we have the hydrochloric, hydrobromic, hydroiodic. These are the lower elements in the halogen family. Lower element in the halogen family. And except this one. Okay, remember HF can form a hydrogen bonding. It holds the proton very, very tight. And we have some other acid. These are the nitrous acid, as opposed to the nitric acid. Nitric acid is strong, but nitrous is weak. And there's sulfurous, so as opposed to sulfuric acid. Sulfuric acid is strong, but sulfurous, because IT ions, these are weaker. And the phosphoric acid in the regular Coke is give a little extra kick, little extra flavor to the soda. This is a hypochlorous acid. It is the effective ingredient in the Clorox. This acid is not strong acid, but it reacts very quickly with the dye molecules. So it basically discolors molecules that has colors. It basically reacts with those molecules and change the molecule shape and change the color. And there are many, many weak acids. Acetic acid is one of the carboxylic acid. Weak acid, but it's good for immune system, as I believe. So that's about a strong acid and a weak acid. What about base? Base, we also have a strong base, weak base. Very similar. The strong base completely becomes ions, and almost none of the molecules stay together. The example will be the sodium hydroxide. The sodium hydroxide, two ions together. Okay. In the solid state, they are together as a one-piece ions. But once dissolving in water, the sodium ion break apart. And all the hydroxide stays free hydroxide, all completely separate. And so that's basically the strong base. The other strong base are the calcium hydroxide. Calcium hydroxide, also a good example. 1 mole of calcium hydroxide, you have 2 mole hydroxide ions. So these are 100% become hydroxide ions. And what are the strong bases? I don't ask you to memorize a strong base, but they are fairly easy to memorize. Are the group 1A, start with the lithium, sodium, potassium, and so on, and a few more. When they form a hydroxide compound, that will give us strong base. So any one of the three with hydroxide will give a strong base. And the other strong base are the group 2A. We call it alkaline earth metals. And start from the lower alkaline earth, lower. So start from calcium, and strontium, and barium. These with hydroxide, each one have a 2+ charge. So when they combine with hydroxide, it is 2 hydroxide with 1 metal ion, the ratio. These are also make it a strong base. So basically we're talking about 6 or 7 strong bases. The number, even the number is very similar to the strong acid. We have about 6 or 7 strong acids, and we have the counterpart, 7 strong, 6 or 7 strong base. There's a few more below potassium. If you have the periodic table, below potassium, we have rubidium and cesium. So about 8-ish strong base. And so when you talk about strong base, these are minority. Strong base, a very good example is the Drano. The Drano, or the drain, what do you call it, drain cleaner, or liquid plumber. They're all based on the sodium hydroxide. They make it a very high concentration so that they can, with high concentration, to unclog, to dissolve the hair fairly quick. You can check, there are many YouTube videos that shows you the hair, human hair, can be dissolved by the liquid plumber, by the sodium hydroxide solution. The concentration for the Drano is about 10%. And if you convert it to molarity, it is for every 1 liter. For every 1 liter, there's about 2.5 moles. So 2.5 m sodium hydroxide. It is used for the drain cleaner. Very strong base. So be very careful with the drain cleaner. It is very reactive and corrosive. It can dissolve the hair. So you can imagine they can dissolve skin. And also they can dissolve the aluminum can, as we've seen from the video. The video last week, Monday, I show you it is aluminum metal dissolved in the drain cleaner. It takes about 1 hour or two, not too long. It'll dissolve the aluminum shell. And inside the plastic bag, that is the insulating the soda from the aluminum, it can stay and finally end up just like a bag. So that's strong base, weak base, all the others are weak base. And there are hundreds of thousands of weak bases. Most weak base are the organic compound. The organic compound with nitrogen in the structure. They tend to be the weak base. And those nitrogen atoms in organic compound, which means the nitrogen linked with at least one carbon. This maybe is carbon, and maybe more carbon. This kind of structure have a nitrogen, and nitrogen here, it behaves like ammonia. So they behave very similar. The ammonia like to take proton from water. Same is for the nitrogen in the organic compound. So the organic compound behave like weak base, or for example, caffeine. Caffeine is a good example. It's actually a weak base. So those weak base, they react with water, but to a very, very low degrees. The equilibrium is highly favor the reactant. Basically means they do not become. So highly favor this. At equilibrium, very few become hydroxide ion and ammonium ion. Most of them stay as ammonia and water. It's highly favor the reactant. So that means they dissolve in water. There's a few hydroxide ions, but very, very few compared with the full strength, the concentration of the compound. So here's ammonia, and we put it into water, and you can see we have 5 ammonia molecules dissolved. Out of 5 ammonia, only 4 of them stays molecules. Only 1, it takes proton from water and turn into the ammonium ion. So these two together formed because ammonia reacts with water. So that makes the weak base.